Hello again, everybody, and welcome back. We're continuing some examples on 2D kinematics and projectile motion in particular. And in this example, we have a dolphin that is a projectile. It's moving up and over, as we're going to see in just a minute, with the intent on catching a ball that is being dropped by a dolphin trainer some distance above. Okay, so let's just go ahead and read this scenario and see if we can make some sense out of it. So a trained dolphin leaps from the water with an initial speed of 12 meters per second. All right, well, I do suggest you draw this, whether you feel like you're good at drawing a dolphin or not, that doesn't matter. Just draw your dolphin and your dolphin trainer and give that dolphin an initial speed or initial velocity of 12 meters per second. I forgot the 12.0 right there, but you can just imagine that's 12.0. All right, so it jumps at an angle and it jumps directly toward a ball that is held by the trainer. So the dolphin is aiming directly at the ball when it is held by the trainer some distance over, that is horizontally, so 5.5 meters away. And it is 4.1 meters above the water. All right, so that's the initial position of the ball, that is 4.1 meters above the water surface. So by the way, the assumption is that the water surface is zero. We call that ground zero or level zero. Okay? So if gravity didn't exist, in the absence of gravity, the problem says, the dolphin would move in a straight line to the ball and catch it, right? Just like this. It would move straight up and catch the ball. And by the way, in the absence of gravity, the ball wouldn't move either, so that would be great. All right, the dolphin would catch the ball, still being held in the trainer's hand. But of course, we know that doesn't happen. We know that the ball drops down, and so if the dolphin were to keep moving up, he would miss it. But thankfully, the dolphin actually winds up moving in a parabolic shape, and that's what the problem says. Because of gravity, the dolphin follows a parabolic path well below the ball's initial position. So even though the dolphin is aiming at the ball, the dolphin's going to take a parabolic path, and the assumption is, and this is what we want to prove, that the dolphin and the ball are going to meet in midair like that. Okay, so that's what we want to see happen. That's the assumption. So remember, the dolphin is aiming directly at the dolphin trainer and jumping out of the water with a velocity of 12 meters per second. Okay, well, let's take this and turn it into some x and y components, because that's the main key to solving 2D kinematics. So we know the y component of the initial velocity is going to be vi, or initial velocity, times the sine of theta, that angle theta. And remember that angle theta is the angle of that initial velocity that it makes with the horizontal. Okay, so that theta is going to be with the horizontal. And then we also know the x component of that initial velocity. The x component is always the full vector times the cosine of theta. So of course that begs the question then, well, what is theta? What is our angle theta right there that it makes with the horizontal? That's one of the first things we want to find out, because in order to find those y and x components, we need to find out what that angle is. Well, we're able to find out what that angle is. This whole scenario makes kind of a right triangle, and the opposite side of that right triangle is 4.1 meters, and the adjacent side is 5.5 meters, and so we can find out what that angle is by taking the inverse tangent. Right? Take the inverse tangent of what is it? The opposite over the adjacent, right? Well, there's your opposite right there, 4.1 meters, and your 5.5 meters is your adjacent. And so the inverse tangent of that will give us our angle theta, and that is 36.7 degrees. So we've found what theta is because we know the horizontal distance and the vertical distance that the dolphin is aiming upwards. Okay? So let's simplify that. Let's put those back and make our theta 36.7 degrees. Okay. Well, what else do we have going on? We know now that since we have that theta, we can plug that in. And so our initial velocity in the x and initial velocity in the y can be found, because we have 12 cosine of 36.7 and 12 sine 36.7. So I'm writing them, or having them show up right here next to the x and y components. You might want to draw them or write them in a x and y in kind of two different columns, and make x and y values in two different columns. Wherever you write them, we're going to calculate them as such. What's the x component? Well, that's going to be 12 cosine 36.7, and that's 9.62 meters per second. All right, what's the y component? That's 12 sine 36.7. That's going to be 7.17 meters per second. So this is the x and the y component of the dolphin's velocity coming out of the water, because that velocity is at that 36.7 degree angle. Okay? So that's good. We have our initial velocity of the dolphin in x and y components. Well, what we want to make sure is the dolphin is at where the ball is when the ball is dropped. All right. So what we really want to find out now is how much time does it take for the dolphin to get to where the ball is dropped. So the ball is dropped 5.5 meters over in the x direction. So really that amount of time is going to be determined by the dolphin's motion in the x direction. Okay, so we want to find that delta t. We want to find that change in time that it takes to get from the dolphin from where it is to where the ball is being dropped. So it's going to be moving over 5.5 meters in the x direction. And since we know the initial velocity in the x direction, and by the way that there's no acceleration in the x direction, we should easily be able to find the time. Now, we have an equation for motion in the x direction with 2D kinematics since there is no acceleration. That is, the displacement in the x direction is simply initial velocity in the x times time. We know the first two values. We're solving for time, so let's just rearrange this and solve for time. Okay, so we have our displacement in the x and our initial velocity in the x. Let's just plug those values in right there. And what do we get? 5.5 meters divided by 9.62 meters per second. That gives us 0.57 seconds. That's how much time it takes for the dolphin to get horizontally from where it is to where the ball is being dropped. It's not going to catch the ball if it doesn't get to where the ball is being dropped. So that's the amount of time it takes to move horizontally in that direction. All right. Well, let's go ahead and just put those back and write that in a little neater manner right there. Okay. So the time that's important to us is 0.57 seconds. We've used the x component to determine how long it takes the dolphin to get there. So that's going to be the critical amount of time, 0.57 seconds. So now let's find out where the ball will be after 0.57 seconds. So the dolphin has gotten to at least the location under the ball, right? It's gotten to where the ball is being dropped in 0.57 seconds. But where will the ball be? Okay, well, it's had a chance to drop for 0.57 seconds, all right? So we're going to write that down, 0.57 seconds for the amount of time for the ball to drop. We know that the initial position of the ball in the y direction is 4.10 meters. That's the height, you might say, the initial position of the ball. Well, what we're asking, is the final position of the ball. That's what we want to find out. Where is the ball going to be? Where in midair is it going to be after those 0.57 seconds? Because again, that's how long it takes a dolphin to get to where the ball is being dropped. So the final position we want to know. The acceleration of the ball, I think we all know that's negative 9.81 meters per second, right? Because it's being accelerated downwards by gravity. And since it's being dropped from rest, we can also say that the initial velocity of the ball is 0 meters per second. Okay, so we have all these values for the ball. We want to find out where the ball is going to be after that amount of time. Okay, so we have an equation. We've got what we call our utility equation sometimes in kinematics. That is, displacement is initial velocity times time plus 1/2 times acceleration times time squared. I have some subscripts in here just so you can kind of keep everything straight. But this is our equation to solve for the final position of the ball. All right, now remember that displacement, delta y, that first value right there, equals final minus initial. Final position minus initial position. So we can write that in. All right, Now we should be able to rearrange things and just solve for that final position of the ball after those 0.57 seconds have elapsed. All right, well, let's move our initial position of the ball over to the right-hand side. We're just going to add it. Okay. And now we can start plugging in our values because we have everything else. So, what's the first thing we're going to do? Well, that initial velocity of the ball, that thing that just flashed right there, what's special about that? Well, the initial velocity of the ball is 0, right? So that whole middle part, time to time, is going to go away. So that's good news to us. So that's just going to shrink down like that. And now we can start plugging in our values. Initial position of the ball is 4.1 meters. I'm leaving off the units just for the sake of simplicity here. All right, 4.1 meters. Plus that half I'm going to turn into an 0.5 because we're going to key this into a calculator, and that might be easier. And of course we know our acceleration of the ball is going to be negative 9.81 meters per second squared, of course. All right, and finally our change in time squared, that's going to be our 0.57, or 0.57 seconds, that value squared. All right, so what happens if we key these into our calculator and crunch all of our numbers? What I get is that the ball is at a final position of 2.51 meters. That means 2.51 meters above the water. All right, so that means the ball is going to be dropping downwards, and this final position right here of the ball is 2.51 meters above the water. And again, this is all after 0.57 seconds. That means the dolphin is going to be at the place where the ball is being dropped at that point. The only question now to answer is the dolphin going to be at the right height? We know the dolphin is going to be somewhere above or below or at where the ball is being dropped, but where is it going to be height-wise? That's the last thing we're going to solve right there. Okay, so we want to find out, lastly, and that was weird how that equal sign kind of came down, what's the final position of the dolphin? We know the dolphin is going to be at that point where the ball is being dropped after 0.57 seconds. But how high is it going to be? We hope it's going to be at the height of the ball so that the dolphin can catch it. Okay, well, some things we know about the dolphin's initial position. Since it's starting at the water level, we can say the initial position of the dolphin is 0. It's starting at 0 level. We also know that the acceleration of the dolphin, and now we're talking just about the y direction now, because we already talked about the x. We know that in the x direction, the dolphin is going to be at the ball. But how high is it going to be? Well, in the y direction, there's going to be an acceleration of negative 9.81. And that's because of gravity. All right, so that's, by the way, that's what's creating this parabolic path of the dolphin, negative 9.81. And of course, we know that the amount of time it takes to get there is, what's that magic number? 0.57 seconds. That's the amount of time it takes for the dolphin to get to where the ball is. So it's the amount of time that the dolphin has to rise up in the air and hopefully be height-wise where the ball is too. Okay, so we're solving for that final position of the dolphin. So all we really need to do is use the same equation that we did before for the final position of the ball. The final position of the dolphin equals the initial position of the dolphin plus initial velocity. By the way, I didn't write dolphin subscript for all these right here. That would take a lot of space. But the initial velocity in the y times time plus 1/2 times acceleration in the y times time squared. All right? So all these values we have, and we can simply substitute in our values and find out what the final position of the dolphin is going to be. All right? So what's the first thing that we know? Well, we know that the initial position of the dolphin is 0 meters. All right, well, that becomes easy, so that just goes away and everything kind of squishes it down like that. Excuse me, I hit my mic. All right, initial velocity of the dolphin in the y direction, right? It's going to be 7.17 meters per second. Let's spread this out a little bit because we're going to need some more space. Our change in time is 0.57 seconds. All right, our 1/2, I'm just going to make, excuse me, 0.5. Our acceleration in the y direction is negative 9.81. And our t squared is 0.57 squared. So this is going to determine the final position of the dolphin in the y direction. We know he's going to be at the ball with regards to the x direction. How high is it going to be in the y direction? The dolphin is going to be 2 0.49 meters above the water, which is almost exactly where the ball is going to be. In fact, it is going to be exactly where the ball is going to be. We're off just because of some rounding issues. But if our two values are off by 200ths of a meter, we can say it's pretty darn close. So this has some applications that we can apply in class and out in the real world. But this is proof that the dolphin is going to hit the ball as long as the dolphin jumps towards the ball when the ball is being dropped. All right. So they're both going to move downwards, and in the middle of the air, dolphin's going to, well, he's not really catching the ball. It looks like he's hitting it with his nose, but he's going to contact the ball because both of those bodies are being accelerated downwards by gravity at the same rate. All right. So that's our example of the dolphin and the dolphin trainer. I'll thank you for following along, and I'll see you on the next one.